Okay, so some driving forces of reactions we have listed here, and we're going to look at all of these. We're going to spend a lot of time on the formation of a solid, which is also known as a precipitate, and we sometimes take that precipitate and we just call it PPT for precipitate, but that's a solid formation, and because of that we need to know the solubility rules, which will be given to you on the test. We will then look for the formation of water, which is also called a neutralization reaction, and that's going to be specifically between an acid and a base. And then one equation we're going to look at is a double displacement reaction that forms carbonic acid, which breaks down to a gas. So we'll look at that one, but there's only one here. So this is going to be most of them right here. And then lastly, we're going to look at the transfer of electrons, which is oxidation reduction, or sometimes we call that redox. Okay, so the first thing we're going to do is look at the formation of a solid, a precipitate. So what you have to know about solubility rules is when you look at a compound to tell if it's soluble. If you have a compound with Na plus 1, K plus 1, ammonium plus 1, hydrogen plus 1, which would be an acid, they are going to be soluble. Soluble means they're aqueous. They dissolve. All right. If you have a compound that contains nitrates or acetates, those are also going to be soluble AQ. And you can actually write AQ down on your solubility table to help you remember that. If you have a chloride salt or a bromide or an iodide, generally those are soluble. Now there are some exceptions that we really have to know about, and those are silver chloride, lead 2 chloride, and mercury 1 chloride. Those three are not going to be soluble, so they're going to form precipitates. So you would put a solid for these, whereas any other chloride, bromide, or iodide you'd put a Q for. Now, this rule pertains to all of the halogens, so Br minus 1, I minus 1, I would follow that same rule. So if I had Br, Br minus 1 with silver, AgBr, I would say that that's a precipitate, or Pb, Br2, that'd be a precipitate, and so on. But if I had anything else Br, I would say, nope, that's soluble. Most silver salts are insoluble. And so what that means is they will be a solid, but there are some exceptions. Silver nitrate, silver acetate, both of those would be aqueous. But otherwise, silver salts tend to be forming precipitates, they're solids. Most sulfates are soluble. Again, those would be aqueous, but there are some exceptions. Barium sulfate, lead 2 sulfate, calcium sulfate, we're going to consider all of those solids. Precipitates. Most hydroxides are not soluble. I would put solid. The exceptions, though, sodium hydroxide, potassium hydroxide, barium hydroxide, calcium hydroxide, all of those we would consider soluble aqueous. And most sulfides, carbonates, chromates, oxalates, phosphates, that's broken off here, are not soluble. So these would all be solids. Okay. Now, this is a pretty black and white way of looking at things. In reality, everything is a tiny bit soluble, and sometimes we talk about slightly soluble or mostly insoluble and all that stuff. But for this level of chemistry, we're just going to go black and white. It is either or is or isn't. Okay? All right, so we have to try to visualize what's going on here. And okay, so let's try to visualize what's going on. If I had a beaker here with potassium chromate, I would have 2 potassium ions and a chromate. So this is my beaker here containing those things. And then I have another beaker, I know these are not good beakers, and I have barium, and then I have a couple of nitrates. And by now you know how those break up. All right, so they're going to dissolve separate beakers. We know from our solubility rules, if I have a potassium salt that's soluble, I know from our solubility rule number 2, nitrates, salts are soluble. Okay, but now what we're going to do, and by the way, those are called strong electrolytes because they break up entirely. They break up in ions when they're in water. They conduct a current. They'd light up that light bulb. Now I'm going to pour this one into this one, and now we have this beaker and it contains a couple of potassium ions, it contains a barium ion, it has a chromate. Of course there's more than just these, but you get the idea. So now we have them all together. So now what we have to say is what is going to happen. And so what is going to happen could be that potassium and it was with chromate and nitrate get together and form a precipitate. The other thing that could possibly happen is that barium and chromate get together and form a precipitate. So those are kind of our questions of what's going to happen. And what we do, all right, we look at our solubility rules. And our solubility rules tell us that potassium and nitrate, both of those, potassium salts, nitrate salts, neither one of those has the ability to form a precipitate. So that's not going to happen. However, if you look at the last rule, chromates do form a precipitate. So we know that that's going to be a solid. I should put it in our solid color here. It's going to form a precipitate. And so what we know from the solubility rules is that when I put potassium chromate together, aqueous, and I put barium nitrate together, aqueous, what's going to happen is what's called a double displacement reaction. Potassium and nitrate, possibility, question mark? And we said, nope, check your solubility rules. That's not going to happen. They just remain, so they're a possibility, but we know from the solubility rules they remain aqueous. But how about barium and chromate? Well, we know from the very last rule that is going to form a precipitate, so that's our solid precipitate. Then the other thing is that we have we have this idea too where I don't take this 2 and automatically bring it over here. You have to be careful. If K is a +1 and it's going to potentially get together with a nitrate with a -1, +1, -1, that's a 0 net charge. So don't drag that 2 over here. The only reason there was a 2 there because chromate is a -2 and K is a +1. That's why there were 2 of them. Similarly, over here I've got 2 nitrates because it's with barium. But here I only have the 1 because it's with a +1. So be careful of that. Now, what we do is something called a net ionic, which I'll talk about in a little bit as well. But the net ionic is really just telling the story of what's happening. And what's happening ultimately is that barium and chromate are getting together to form a solid. Nothing happened with the potassium and nitrate. They were free single ions before, they're free single ions afterward. No commitment, no getting together, nothing happened. All right, so what it's called is a double displacement reaction. Partner switch sometimes. The charges do not change, the partners change. After they switch, they do a 0 net charge with their new partner. So you have to be careful. So the first thing you want to do is just make sure that they have this +1, -1, aqueous. Look at rule number 1. Iron 3 nitrate is also going to be aqueous. Look at rule number 1. Or 2, sorry, rule number 2. So we know there's going to be aqueous. Now after the reaction, the possibilities are this cation potassium is going to go with this nitrate anion. All right, so we have a potential KNO3 +1, -1. But we know from the rule number 1 here, rule number 2 there, if that wasn't enough, that they don't do anything. They do not form a precipitate. So now let's see if the other one does. Does iron and hydroxide? Yep, if you look at the very last rule, there's no rule about iron per se, but there is a rule about hydroxide. And hydroxides are precipitates, so that's a solid. Also notice I do put a 3 here because it's now with iron. Iron's a +3, it's a -1. There's going to be 3 of them. And there's not 3 nitrates. It's just KNO3 because K is a +1, NO3 is a -1. Don't drag that 3 over here. There's not 3 nitrates. Okay? Now we do want to balance this equation. And so what we'd probably do is put a 3 and a 3, and that would balance it. If you were to do a net ionic, we'd say iron with a +3, 3 hydroxides, each with a -1, makes this precipitate. We leave out anything that stays aqueous. It was aqueous before, aqueous after, we just leave it. This is our net ionic. All right, so one more example before I end this. I've got sodium sulfate, aqueous, rule 1, mixes with lead 2 nitrate, aqueous, rule 2. Partner switch, lead, which is a +2, is going to get together with sulfate, which is a -2. That's a 0 net charge. And the other possibility, if anything happens, is sodium getting together with nitrate. And again, rookie mistake is to drag this 2 over. Don't do that. +1, -1. Now we look at our solubility rules, and we see rule 1 and rule 2 rule that out. But if you look at the sulfate rule, a lot of sulfates are aqueous, they're soluble. But there's an exception, or a couple exceptions, and one of those exceptions is lead 2 sulfate, and that does form a precipitate. All right, we would definitely want to balance by putting a big 2 there. Net ionic is Pb +2, sulfate -2 makes PbSO4. That's our net ionic. That's what really happened. Aqueous sodium was aqueous before, nitrate was aqueous before, afterwards they're aqueous. They don't do anything. But lead's a +2, sulfate's a -2, they get together, they form it. Okay. All right, so I kind of talked about this net ionic, and I'll talk a little bit about it more in the next